Welcome to the Deep Dive, the show that extracts the crucial nuggets from the latest research. Today, we're diving into something generating huge excitement, especially in social science. Large language models, LLMs.
Right. They promise so much, like automating really labor-intensive stuff, data annotation, text analysis, on scales we just couldn't manage before.
It sounds amazing, all this data suddenly unlocked.
Exactly. Think about pulling insights from, I don't know, mountains of social media posts or maybe political texts super fast. The enthusiasm is definitely there.
Okay, sounds like a researcher's dream. But there's a catch, isn't there, to twist?
It is a pretty significant one. Underneath all that potential, there's this critical threat to, well, scientific validity that hasn't gotten much airtime. People are calling it LLM hacking.
LLM hacking. Okay, my mind immediately goes to security breaches, but that's not what we're talking about here, is it?
No, not at all. It's more subtle. LLM hacking, in this context, is basically when the choices researchers make in setting up these models, configuring them, end up leading to wrong conclusions in their actual analysis later on.
Ah, so it's about the setup influencing the results.
Precisely. It's not just a small error in measurement. It's a systemic weakness right at the data generation step.
Got it. So our mission today is to really unpack this. What is LLM hacking? How does it skew results, sometimes subtly, maybe sometimes obviously?
And, importantly, give you some practical, evidence-based ways to navigate these risks. We're basing this heavily on a really large-scale study.
Oh, yeah. Tell us about the scale of this research. It sounds like they really went deep.
They did. It's impressive. They replicated 37 different data annotation tasks. These came from 21 published social science papers, and they used 18 different LLMs.
18 models. Wow.
Yeah, and analyzed something like 13 million LLM-generated labels, all to test over 2,300 hypotheses. So this isn't just theory. It's a serious empirical look at what happens when these models generate research data.
Okay, let's really get into it then. LLM hacking. You said it's about the choices researchers make.
That's the core idea. The choices made when configuring the LLM lead to incorrect scientific conclusions downstream. It's a vulnerability baked into the process.
This sounds a bit like p-hacking, where researchers might tweak their analysis to get a significant result. Is it similar?
That's a great comparison, actually. It's analogous, but different in a key way. P-hacking messes with the analysis choices. LLM hacking happens before that.
Ah, okay.
It's at the data generation stage. So it creates this whole new layer of potential problems before you even start running statistical tests.
Can you give us an example? Make it concrete. How can one choice flip a result?
Sure. Let's take a common task.
Yeah.
Figuring out if a political text, say a manifesto, leans left or right. Imagine a situation where, in reality, there's no actual difference, no true effect. The real p-value is, say, above 0.05, not significant.
Okay, so nothing's really going on there.
Right. But the study found that just by changing the LLM configuration, maybe using the same LLM but with a slightly different prompt or parameter, you could go from a non-significant result like p equals 0.242
Still nothing?
to a highly significant p equals 0.001. Same data, same underlying reality, but the LLM configuration flips the conclusion. You suddenly think you found something that isn't there, a false positive.
Wow. Just from tweaking the LLM setup, that really highlights the hidden risk. What are these choices then, these researcher degrees of freedom? You mentioned a garden of forking paths.
Yeah, the garden of forking paths is a good way to put it. Researchers face a ton of choices.
Yeah.
Which specific LLM model do you use? How exactly do you write the prompt, the instructions? What about decoding parameters like temperature?
Yeah.
That controls randomness.
Temperature.
Yeah, basically how creative or predictable the model's output is.
Mm-hmm.
And then there's how you map the LLM's text answer. Maybe it gives a paragraph back to a simple category like left or right.
Mm-hmm.
Each choice is a fork in the path.
And you don't know where each path leads.
Pretty much. And the scary part is, even tiny, seemingly insignificant changes can sometimes have these huge, unpredictable effects on the final results.
And this can lead to different kinds of errors, right? Not just getting it wrong, but how you get it wrong.
Exactly. The study talks about four main types. There's type I error,
Yeah.
the false positive we just talked about, finding something that isn't there.
Right.
Then type 2 error,
Mm-hmm.
a false negative, missing an effect that is actually there.
Okay, missing something important.
Then there's type S error, which is pretty alarming.
Mm.
That's when you correctly detect there's an effect, but you get the sign wrong.
Wait, the sign? You mean like finding a positive effect when it's actually negative?
Precisely. Imagine a study concludes a policy helps something when the LLM data actually, if interpreted correctly, shows it hurts. That's a type S error.
Yeah.
Terribly misleading.
That sounds dangerous. What's the last one?
Type M error. That's magnitude error. You get the effect right, You get the direction right, positive or negative, but you get the size of the effect wrong. It's either way bigger or way smaller than reality.
So you might think something has a massive impact when it's really tiny, or vice versa.
Exactly. These aren't just academic footnotes. They can seriously mess up our understanding and any decisions based on that research.
Okay, that's a clear picture of the potential problems. Now, the big question, how often is this actually happening, this accidental hacking?
Well, prepare yourself. The numbers are pretty stark. The study found incorrect conclusions cropping up in about 1 out of every 3 hypotheses when using the best state-of-the-art models.
1 in 3, even with the best models.
Yep, and it gets worse. If you use smaller language models, that risk jumps to half the hypotheses.
Half. Wow. So if you're reading social science research using LLMs now, there's a non-trivial chance the findings are skewed just by the model configuration.
That's what the data suggests. It really makes you question the reliability of some of this output.
Is the risk the same for all kinds of tasks, or does it depend on what you're asking the LLM to do?
It definitely varies. It's not flat across the board. For some tasks, maybe like detecting if a text is humorous, the risk might be down around 5%.
That's lower.
But for more complex things like classifying political ideology or identifying specific frames in text, the risk can shoot up to over 65%. So complexity matters, but importantly, no task seems totally safe.
Right. So what about model quality? If I use a really good LLM, one that scores well on benchmarks, does that solve the problem? Is there a point where it's just good enough?
That's what you'd hope, right?
Ah,
And yes, better models, ones with higher performance scores like F1 scores, do tend to have lower hacking risk. That makes sense.
okay.
But, and this is big, but they don't eliminate it. Not even close. The study found models with fantastic performance, like 93% F1 scores, could still have hacking risks over 50% for certain tasks.
Over 50% risk, even with 93% accuracy. How does that work?
It shows this really important disconnect. Good annotation performance doesn't automatically mean your downstream scientific conclusions will be valid. They're related, but not the same thing.
That's a critical point. Performance scores aren't the whole story. What about the types of errors? You mentioned type I, 2, SM is one more common than others.
Generally, yeah. Type 2 errors, missing true effects, seem to be the most frequent issue. So LLMs are maybe more likely to overlook real differences than to invent fake ones.
Okay, so they err on the side of caution, maybe?
Sort of, but it's still a problem if you're missing real findings.
Yeah.
And even when they do correctly find an effect, there's the type M error issue. The estimated effect sizes are often way off.
How far off?
On average, the study found they deviate from the true values by 40 to 77%.
40 to 77%, that's huge. So even if you get the yes-no right, the how much could be completely wrong.
Exactly. Which means just using bigger, better models isn't a magic fix for getting reliable effect sizes. The distortion persists.
This is, yeah, quite concerning. So what's the practical advice then? For researchers, or maybe even people using these tools in business, how do you minimize this accidental hacking?
The core recommendation is pretty straightforward. Use the most capable models you can access. Generally, bigger models tend to be more capable.
Like the ones with billions of parameters.
Right. The study showed models with, say, 70 billion plus parameters had around a 31% hacking risk on average, compared to about 50% for much smaller models, like 1-2 billion parameters.
So bigger is better, generally.
Generally, yes.
Yeah.
But crucially, don't expect miracles. You get diminishing returns. Just scaling up the model size won't make the risk vanish entirely. It helps, but it's not a complete solution.
Okay, that makes sense. Which brings us to something maybe even more disturbing, intentional LLM hacking. If it's this easy to mess things up by accident, what if someone wants to?
This is where the study gets, frankly, quite alarming. They found that intentionally manipulating results using LLMs is, well, they called it unacceptably simple.
Unacceptably simple. How simple?
With just a few different LLMs and maybe tweaking the prompt slightly, you can apparently make almost anything look statistically significant.
Anything, really. Can they put numbers on that?
They did. And the numbers are pretty shocking. They found that someone trying to cheat could manufacture false positives find an effect where there is none for 94.4% of null hypotheses.
94%. Okay.
They could hide true effects, cause a type 2 error in 98.1% of cases.
Hide almost anything.
And maybe, most worryingly, they could take a real effect and completely reverse its direction, a type S error, in 68.3% of cases, while making the whole analysis still look scientifically credible.
Reverse the finding in 2/3 of cases. And make it look legitimate. That sounds like a recipe for scientific chaos if someone wanted to abuse it.
It really does. And the problem is detection.
Yeah, how would you even know if someone did the... Can you spot it afterwards?
That's the kicker. The study says the difference between a genuine analysis and a manipulated one becomes virtually undetectable post hoc, after the fact.
Undetectable.
Pretty much, meaning someone with bad intentions is almost guaranteed to succeed without getting caught. Even if they only use the top-performing models, the potential for manipulation stays disturbingly high.
Wow, okay, if it's undetectable, then the only defense seems to be transparency before it happens. What's the recommendation there?
Absolutely, transparency is key. Researchers need to document everything. All the models they tried, all the prompts they used, not just the one that gave the result they published.
Show your work, basically.
Exactly. And as a peer reviewer, or even just a reader, you should be a bit suspicious if a study only reports results from one single LLM setup without explaining why that specific one was chosen.
Makes sense.
The study strongly pushes for pre-registration. Before you even run the analysis, you publicly state, I will use this model, these prompts, these parameters. That makes it much harder to cherry-pick results later. It should become standard practice.
Pre-registration for LLM choices, that seems like a necessary step.
Okay, so we know it can happen accidentally or intentionally. Where is this vulnerability greatest? Are there specific situations where LLM hacking is more likely?
Yes, there are definite predictors. The biggest one, how close the result is to the standard significance threshold, usually that p 0.05 line. Ah, the borderline results.
Exactly. Results hovering right around p 0.05 are found to be extraordinarily unreliable. The error rates can approach 70% in that zone. So if you see an LLM-based p-value that's like 0.04 or 0.06, that should be a huge red flag. It's an observable warning signal.
Okay, so be extra skeptical of borderline findings, but what if the p-value is really, really small, like 0.0001 or really large? Can we trust those more?
You'd think so, but here's another crucial finding. The risks remain high, even when p-values are far from 0.05.
Really? Even for seemingly strong results?
Yes. Type I, Type 2, and especially Type S errors can still pop up quite frequently, even with p-values that look decisive. This means LLM errors aren't just blurring the lines on borderline cases. They can actually obscure or even reverse findings that should be robust.
That's quite profound. It means even a statistically strong result from an LLM might be misleading.
It can be. It's not just noise near the threshold. It seems to be a more fundamental issue with how these models generate the data for analysis.
So what's the advice for us, for the listeners, when we see any LLM-based result?
Exercise extreme caution, basically. Don't just focus on whether p is less than 0.05. Treat all LLM-derived conclusions as preliminary findings that really need validation, ideally through other methods.
And for researchers?
They should run sensitivity analyses, try multiple models, multiple prompts, see how much the results bounce around, and crucially, report the whole picture, the distribution of findings across different setups, not just a single number from the best one.
Right, show the uncertainty. Now, a lot of talk in the AI space is about prompt engineering, getting the instructions just right for the LLM. Does that help much with this hacking risk?
You'd think it would be a major factor, wouldn't you? But the study found something surprising.
What's that?
Prompt engineering choices, like using few-shot examples versus zero-shot, or detailed instructions versus brief ones, accounted for less than 1% of the variation in LLM hacking risk.
Less than 1%. So tweaking the prompt isn't the magic bullet.
Apparently not for avoiding hacking risk directly. Now, good prompting can improve the LLM's performance overall, which indirectly helps reduce risk because better performance is correlated with lower risk. But prompt choices by themselves aren't preventing the hacking phenomenon. It's not the main lever.
Interesting. So what's the practical advice on prompts then, given that?
Well, the study still suggests it's generally better to prefer few-shot prompting, given the LLM examples, over zero-shot, and use detailed task descriptions. It helps performance, which is good, but just don't expect it to solve the hacking problem on its own.
Okay. And what about the tasks themselves? We said risk varies. Does it correlate with how well humans agree on the task? Like, if humans find a task easy and agree perfectly, is the LLM safer?
That's another counterintuitive finding. While risk definitely varies a lot between tasks, remember 5% for humor versus 65% for ideology.
Right.
There was no significant correlation found between LLM hacking risk and human inter-annotator agreement.
Wait, really? So even if humans agree 100% on how to label something, the LLM using that task could still produce unreliable downstream results.
That's what the data indicates. It means you can have a task where humans are perfectly consistent, but LLM-based conclusions from that same task could still be highly susceptible to hacking errors.
That totally goes against what I would have assumed.
Yeah.
So what's the takeaway for researchers there?
The big one is, do not rely on high human agreement to decide if it's safe to use an LLM. Just because humans find it easy doesn't mean the LLM will generate data leading to valid conclusions. You have to validate the LLM's performance specifically for your task and, crucially, for your downstream analysis, regardless of how well humans agree.
Wow. Okay, this paints a pretty challenging picture. We have accidental risks, intentional risks, problems even with good models and easy tasks. So what actually works? What are the most effective ways to mitigate this?
Well, the study's findings on mitigation are quite clear and maybe a bit surprising. It leads to what they call the LLM data scale paradox.
Okay, I'm intrigued. What's the paradox?
Get this, 100 human annotations outperform 100,000 LLM annotations when it comes to controlling type I errors, false positives.
100 humans beat 100,000 LLM labels.
For type I error control, yes. The 100 human annotations reduced the risk to around 10%, whereas hybrid approaches using LLMs were still up around 30–38% risk. It just highlights how powerful it is to avoid LLM-specific biases altogether.
That really is a paradox of scale. Smaller, high-quality human data is better than massive LLM data for reliability. So the practical advice is,
Pretty simple. Collect as many expert human annotations as you possibly can. Just using a random sample of purely human annotated data gives you really strong protection against false positives, much better than relying on LLMs or even hybrid methods.
back to basics in a way, but what if you can't get enough human annotators? What about those statistical correction techniques people talk about? Can't we just mathematically fix the LLM's mistakes?
There are techniques, yeah. Things like design-based supervised learning, DSL, or confidence-driven inference, CDI, and they can help. They can reduce type I errors.
Ah, okay, so there is a fix.
Well, it's a trade-off, a big one. While these methods reduce false positives, type 1, they significantly increase false negatives, type 2 errors,
How much?
by up to 60 percentage points.
60. Wow, so you fix one problem but make another one much worse.
Exactly. It's a fundamental dilemma. You're basically choosing which kind of error you're more willing to live with.
So how do researchers make that choice?
They need to choose correction methods based on their specific research goals. If you're exploring brand new ideas, maybe avoiding false positives, type Y is paramount. If you're trying to replicate existing findings, maybe missing a true effect, type 2 is the bigger concern. There's no single best way. It depends on the context.
And if you do use LLMs, is there anything else?
Yes. If you use LLMs, selecting the model based on its performance on a small, human-annotated validation set for your specific task offers some extra protection. It reduces risk by about 4 percentage points compared to just picking a popular model like GPT-4o off the shelf.
So testing the models on your own human data first helps a bit. But the overall message seems pretty strong.
It is. The most effective strategy they found, bluntly stated, was essentially abandoning the use of LLMs entirely and just collecting human samples. That offered the best protection against these errors.
That really turns the whole LLM hype on its head, doesn't it? Okay, so wrapping this up, what's the big picture takeaway for the future of using LLMs in research?
It really calls for a fundamental shift in how we approach LLM-assisted research. We absolutely have to move away from treating these models as just convenient plug-and-play black box annotators,
And see them more as
complex scientific instruments that require careful calibration, rigorous validation, and an understanding of their limitations, just like any other scientific tool.
And it sounds like the human touch isn't becoming obsolete anytime soon.
Not at all. The study makes it clear. Human annotations and task-specific validation are still indispensable. Purely LLM-based approaches, at least for now, consistently underperform strategies that actually leverage human expertise, especially for ensuring the validity of the final conclusions. LLMs give you scale, yes, but humans still provide that crucial ground truth.
That's a powerful, maybe even sobering conclusion. It definitely makes me think differently about studies using this tech. So maybe a final provocative thought for you, our listener, to chew on. The study mentions this idea of multiverse LLM annotation approaches.
Right, the multiverse idea.
Instead of just giving one result, imagine researchers had to report the entire distribution of findings, say, the range of effect sizes across all the reasonable LLM configurations they could have used. What would that kind of radical transparency about the inherent uncertainty mean, not just for LLM research, but for how you evaluate any analysis or information you come across? How might thinking about that garden of forking paths change how you critically look at the world? Something to ponder.
And a really interesting thought to end on. Thanks for joining us for this deep dive into the tricky world of LLM hacking.
And thank you for listening to The Deep Dive. We'll be back soon with more insights from the latest research.